Now, our next speaker, I don't even get to introduce. I'm going to hand that over to Taryn Noble from the Royal Society of Tasmania. Taryn, take it away.
Hello everyone, I'm Taryn, and it's a pleasure for the Royal Society to present Associate Professor Barbara Holland's talk to you tonight. I just wanted to give you a couple of seconds spiel about what the Royal Society is, because perhaps many of you don't know who we are. So the Royal Society of Tasmania is actually the first Royal Society that was established outside of the UK, the second one being Edinburgh, and the third one being the Royal Society of Tasmania. So that makes it Australia's oldest scientific organisation. And it was instrumental in the early days of Tasmania as a colony, establishing the Royal Botanical Gardens, for example, this fabulous museum that we're currently meeting in. And this museum houses a huge collection of colonial art that the Royal Society has collected over the years. And so we meet as an organisation every first Tuesday of the month. And so we have a range of speakers, from speech pathologists to educationalists to scientists. So we encourage you to look us up and come along. And on to the most important thing tonight, which is why you're all here. It's a pleasure to introduce Associate Professor Barbara Holland. You can't get up yet because I have some nice things to say about you. So as a young researcher, which is what I am, I've had a few wonderful interactions with Barbara. She's a fantastic academic, a huge accolade of fellowships and very prestigious grants that she's won. And she's really a fantastic role model to young researchers like myself. She's approachable and, as you'll hear tonight, an excellent science communicator. And I can't imagine anyone better to come and celebrate science and inspire you all than Barbara. She's a statistician. She's working in the Department of Mathematics. It's a bit complicated how it's all structured, but she's in mathematics, and she did her PhD in mathematical biology in New Zealand at Massey University, and she's been in Tasmania for a wee while. And I'll just read you what she says she does, because I couldn't say it any better than she's actually written it. So bear with me while I read it, and then I promise I'll pass on to Barbara. So since beginning her PhD, she's enjoyed the challenge of working with biologists in trying to translate problems they face into the language of mathematics. Biology is awash with data since the advent of DNA sequencing technology, and this has opened up a range of very interesting research questions that require a combination of skills from mathematics, biology, and computer science. And who best to do it but Barbara? So over to you.
Wonderful. Thank you very much, Taryn. That was a lovely introduction. All right, so here we are. There's a lot of you out there. I did this Beaker Street last year, and I got put as the warm-up act to David Walsh. And I thought, this year's surely got to be easier than that. But in fact, I'm sharing the session with a cyborg. So let's see how it goes. Anyway, what are we doing for the next 15 to 20 minutes? What I would like to do is to introduce you to my great friend here on the screen behind me, the normal distribution. Witness its beautiful, woo, yeah, let's hear it for the normal distribution. Beautiful, beautiful, shapely curves. That's right. So some of you might be asking, well, some of you might know this creature actually better by another name, the bell-shaped curve. So if you're sitting there thinking, what's a normal distribution? Bell-shaped curve's another thing you might have heard. And so what is a distribution anyway? So we'll all be aware that life is sometimes filled with uncertainty, chance, randomness, perhaps even sometimes misfortune, and we need a way to try and marshal this randomness and understand it. And a distribution is a way of doing that. It could be something pleasant. You could buy a packet of M&Ms, rip the top off and shake them out on the table, count how many blue, green, yellow, red ones you have. That would be a marvellous example of a distribution. The one I've got up on the screen behind me is much more morbid, fortunately. So this lady here is Florence Nightingale. Has anyone heard of Florence Nightingale? Yes. And so the distribution that she was particularly interested in was causes of mortality during the Crimean War. And what we have up here is perhaps the very first instance of an infographic. So what she was trying to do is make a bit of a point to the politicians back home in Britain that the major cause of mortality in the Crimean War was not being hit by cannonballs or nasty things that happened to you on the field of battle. That's the sort of, you can't really see the colours here very well, but this red bit here is dying in normal warlike ways, but the much larger bit is being killed off by preventable disease. And so she was interested in this distribution of how do people die and how did that change with time. And so this was back sort of the end of the 19th century. And it was a really interesting time because it was really the dawn of this whole idea of statistics and the idea that we might collect data and try and look at what it was like. And as people started to do this, something a bit weird started to happen. What happened was the same shape kept popping out at them. And so I apologise, I haven't been able to source all vintage 19th century data sets, but here's a few I have found. So this one, birth weight in kilograms. We see that we have most babies about 3 kilograms, we have some heifer babies, we have some scrawny babies, but most babies are kind of around the middle, and it has this characteristic beautiful shape. Heights of adult criminal men in Britain, similar sort of a shape. SAT scores in America, maybe a slight lilt to that one, but it's suggestive of being the same shape. Blood pressure, that one's a bit noisier, but if you squint or if your eyesight isn't that good and it looks blurry, that same shape jumps out at you. Female shoe size, similar. This last one, anyone see anything wrong with that? So this one is test scores for high school in Poland. There's one compulsory unit that every student needs to pass, basically a language course, and the cut-off mark for being allowed to do further study is this one here. So it was really trying to be a normal distribution, and then some of the kind teachers probably helped a few students on their way, which to anyone in my second year class who's in the audience, you can be sure that I will support you like this as well. Right. So when I agreed to give this talk, they sent strict instruction. They said, have no slides that are just a wall of text. So I ignored that completely because I love this quote, and I'm going to read it out to you. So this is by Francis Galton, and he was one of the first person to start collecting data sets and look at them and notice this regularity. It's pretty blurry, isn't it? So, okay, let's give it a go. I know of scarcely anything so apt to impress the imagination as the wonderful form of cosmic order expressed by the law of the frequency of error. That's what they called the normal distribution back then. The law would have been personified by the Greeks and deified had they known of it. It reigns with serenity and in complete self-effacement amidst the wildest confusion. The huger the mob, the greater the apparent anarchy, the more perfect is her sway. It is the supreme law of unreason. Why does no one write like this anymore? Isn't this fantastic? Whenever a large sample of chaotic elements are taken in hand and marshalled in order of their magnitude, an unsuspected and most beautiful form of regularity appears to have been latent all along. And so where is it coming from, this beautiful regularity that Galton noticed? How do we get from randomness to the same beautiful pattern? So let's try something. Let's take a dice. You can't get much more random than a dice. If we throw a dice a few times, different things can happen. We get some 1s, some 3s, some 4s, some 6s. Not much beautiful regularity happening yet. Let's throw it a few more times, maybe 100 times or 1,000 times. We're still not getting that shape pop out at us. It's starting to level off. You're getting, I guess, closer to the truth of a fair dice. 1s, 2s, 3s, 4s, 5s, 6s, about equally likely. But it's not what we're after. So let's try something different. Let's roll 3 dice and add them together. Do I have any Dungeons & Dragons players in the room? Go on, admit it. You love this distribution, right, don't you? This is the character generation distribution. Fantastic. So we do it a few times, not much pattern. Let's do it 100 times. Let's do it 1,000 times. Now we're starting to see something. It's not quite got that beautiful shapely curve yet, but it's getting there. So let's go mad. Let's take 30 dice. Roll them, add the faces together. Let's do that 100 times, 1,000 times, 10,000 times. And now we see it. It's starting to pop out at us. The normal distribution is there. And so the fact that this happens is one of the most famous results in all of statistics. It's called the central limit theorem. And the very cool thing about it is it doesn't really matter if you do this with dice or if you do it with any distribution at all. If you take enough, 30 or so, things independently from some distribution and add them together, you will get this shape. It's weird, but it always happens. So I can tell what you're asking yourself right now. You can say, we're 10 minutes into this talk. Barbara's obviously pretty keen on these distributions, and Galton, like, they obviously got his rocks off as well, but how am I going to monetize this? How can we make money out of a normal distribution? Fear not. I would like you to imagine yourself in 1982, and you work as the advertising campaign manager for a cheap and nasty American beer called Schlitz. And you, in your wisdom, have come up with the following advertising plan. You're going to find 100 people who think your beer is shit and prefer a different beer, maybe Miller, maybe Bud Light, doesn't matter. They like some different beer, and you're going to take them and you're going to blindfold them, and you're going to make them taste your beer, which they claim to hate, and their beer, which they claim to like, and then you're going to count how many actually prefer your beer. And because you're very, very, very confident, you're going to pay in inflation-adjusted terms some several millions of dollars, and you're going to do this at the halftime show of the Super Bowl. This is not a joke. This actually happened in 1982. Does this seem like a great idea to people? You're feeling a little nervous? Why have we spent $1 million to do this? This is crazy, right? But you know two things. The first thing that you know, very important, is that all cheap beer tastes the same. Right? All cheap beer tastes pretty much identical. Beer companies don't like to admit this, but they know it's true. The second thing you know about is the central limit theorem. And so if all cheap beer tastes the same, you taste one beer and another beer, what's the chance you say you like one in particular? It's a coin toss. It's a flip. It's just 50-50. So it's a beautiful little random distribution. We pick our 100 people. They are independent draws from this random distribution. We count them. That's the same as adding things together. So we know what it's going to look like. And it's going to look like this distribution here. And so most of the time, about 50 people will say they prefer your beer. If you're really unlucky, maybe only 40 people will say they prefer your beer, but it's never going to be 30 people. And so even if it's only 40, you still look bloody good because these people started off saying that they thought your beer sucked. So this is how you can sort of use statistics to do fun things. All right, now I promised to talk a little bit about the election. So let's warm up by thinking first about an imaginary country. So in our imaginary country, we've got an election coming up. One candidate is Bob. Bob is sort of bland. It doesn't have a very catchy slogan. It's vote Bob, okay? Our other candidate is Cthulhu. Cthulhu has a much better slogan. Vote Cthulhu, why choose the lesser of two evils? It's a perfectly reasonable point. And so let's imagine that in this country, 52% of the population prefer peace and kindness, and they support Bob, and 48% prefer Cthulhu. And this country loves polls, because who doesn't love a good poll? And so every so often they'll take a poll of 1,500 people and ask them how they're going to vote. Let's further imagine that in this country there is no such thing as a swing voter. Like, it's always just that 52% of people prefer Bob and 48% of people prefer the demon Lord Cthulhu. And the country loves polls because they give you something to talk about in the media, and so they take heaps of them. And so let's look at what would happen, sorry this is very blurry, with the last 5,000 polls. It looks like this beautiful normal distribution we've seen before, and what's smack in the middle of it is the truth, 52%. That's the most common value, but also you can certainly get cases where it's a close-up here of the last 50, but easier to see. So you often get exactly 52% coming back in this poll, but you can also get 51 or 53 or 49 even, or 55. So, but usually you're within plus or minus 3%. That's known as the margin of error. You've probably heard of the margin of error. And so you get this perfectly normal shape, and you get this spread of things that can happen. So let's now think about our country, Australia. Don't we love Australia? Do we love Australia? Oh yeah, Australia. 17 polls in a row leading up to the last election, and they were all pretty much identical. They all said 51 or 52% two-party preferred Labor and about 48% to Cthulhu. Sorry, I mean Scott Morrison. So what happened in the actual election? Obviously, well, it didn't quite turn out that way for Labor, did it? It was about 48% support for them. And, well, that's already weird because it's a big bias. But that wasn't the weirdest thing to a statistician. It's not so weird that you can be wrong because sampling well is difficult and you can never get a perfectly representative sample and you have to re-weight and correct for things, so you know you can be wrong. But what was really weird was the fact that you got 17 polls in a row that said the identical thing, because you just do not expect that to happen. So I've just done here sort of a bunch of sort of simulations of 17 polls. They bounce around all over the place. What we had was 17 things in a row in that middle band, no variation. It's called sort of under-dispersal. And that should basically never happen. Statistically, it should just never happen. So what maybe is the explanation? So was it Rubbish Day today for anyone? Rubbish Day, not in any part of Hobart. Well, it was for us over there at the back. So if it's me and I'm putting out the rubbish, I wander out, I put my bin out, and then I'm going to go back inside and I glance to the neighbours. What do I see? I'm like, oh, shit, is it recycling week? I could have sworn it was recycling last week. Is it actually? Oh, I'm sure they're right. And so I go back and I get my recycling bin. And then if you come out half an hour later, the whole street's got their recycling bin out. Doesn't matter if it's actually recycling week. This is a failure of independence, right? This is called herding. Herding. It's like what you do with sheep. Instead of people making their own decisions independently, they're being influenced by what's going on around them. And to me, this is really the only reasonable explanation of the polling results leading up to the election, that the different polling companies must somewhere in their algorithms not just have been reporting an independent result, but somehow looking around at what the other companies were doing. So now if you indulge me, I'd like this. Can anyone see this image? It's so blurry, it's not as outrageous as I hoped it would be. There we go. But anyway, it's an image of a famous artwork from Mona. And I think that this artwork, I love this artwork, it's one of my favourite things at Mona. I go and stare at it all the time. And the reason is not that I'm a filthy perv, although that may be true as well, but the reason is that I think it has an important statistical point to make. It does, because we often ask ourselves in life, what's normal? Am I normal? Are my children normal? And we sort of have this feeling that we should be maybe conforming more to the herd. But what any good statistician will tell you, and what this artwork suggests, is that normal is not any one thing. Normal is a distribution. Okay? Normal is a range. It's a spread of different opinions. And it's really when we all try and be too alike that we get problems like the last polling disaster. So I've got a few credits here. Basically, where did I nick bits of this presentation from? Brian Schmidt, he's the Vice Chancellor of ANU, had a really great article about the polls. Kevin Bonham, our local homegrown polling guy, has a great blog. I stole the wheelie bin example off Richard Corey from uni, and various other websites. And of course the title from Jeanette Winterson, Why Be Happy When You Can Be Normal. Thank you very much.
Ladies and gentlemen, Barb Holland. Give it up for Barb Holland. I reckon we've got time for a couple of questions. I'm looking around at the audience while someone's talking about probability and statistics. I never dreamed I'd see everyone... What's she going to say next? How come she knows this stuff? Who's got a question? Okay. Well, while you're thinking of a question... All right, here you go.
Do you play D&D?
I used to play D&D a lot. My dad was actually the head of the Tikawiti High School D&D Society, which in its heyday had 30 members, which is 1 in 100 of the whole people that lived in Tikawiti, as long as you didn't count the sheep.
Any more D&D questions? I've got a question. Barb, are there any types of data that don't conform to the bell curve?
Oh, absolutely, yeah. There are many other distributions out there that would be wonderful for a sequel talk at next Beaker Street, no doubt. Yeah. Yeah.
Can we get the pithy version now?
So actually, I mean, several of the distributions there are really the binomial distribution in disguise as the normal distribution. So that's one where you have fixed trials and fixed probabilities of success. The Poisson distribution is another really lovely one for describing rare events, and that has a great little story to do with the Crimean War as well, that it perfectly models the number of Prussian cavalrymen that got kicked to death by their horses. Statisticians love to find gory examples for their distributions.
Is there a theme emerging here that we know a lot about this kind of distribution from warfare?
I think examples come from everywhere. And that's one of the wonderful things about statistics once you get obsessed by it, is you see it everywhere. Yeah.
Any other questions? Thank you very much, Barb. We'll let you go. Big hand.